3.1 Permutations with identical elements. So up until now, we have looked at how to find the number of arrangements, permutations, when we were dealing with distinct elements. But what happens if some of the elements we need to arrange are similar? Okay. So you may have noticed a couple of these questions appear on our practice test from chapter 2, and we just have to ignore them. But now I can show you how we can answer those kinds of questions. So permutations with like elements. So investigate. So let's compare the different permutations of the word walk with the word wall and then the word LALL. Okay, so if you look at the word walk, how many ways can we rearrange the four letters in the word walk? Well, here are all of those permutations. Okay, so if we simply do 4P4, we can find the total number of permutations, or you can just count them in here. Or we can just say 4 factorial, which is 24. Okay? So we have 24 different ways of arranging these four letters in the word walk. Okay, and it's 24, and remember they're all unique letters. Okay, these are all unique letters, so we have a unique number of arrangements. Now, what if instead of the word walk, we did the word wall? All right, and so here are all the arrangements of the word wall, but to do it this way, you have to treat the two letters L and L as distinct letters. So that's why we have to denote them L1 and L2. Okay, just to show that we have 24 permutations. But really, these L's are the same letter, and you notice that this word wall repeats over here, and this WLAL repeats over here, WLAL, and then WLLA repeats over here, WLLA. Okay, so of the original 24 permutations, only 12 of them are different. Okay, I'm just going to quickly highlight. So this is the same as this. Okay, this is the same as this, and this is the same as this, and this is the same as this. So really, out of these pairs of columns here, I can only count 4 of them. I can only count these 4, and I can only count these 4. So really, it's a 24. Only half of them are the same. Okay, so really 12 of them are different. So because of this repeating letter, okay, the repeating letter. So there are arrangements that look the same because of the repetition of the letter L. Since two L's can be placed in 2 factorial ways, sometimes we just say 2 ways, okay, the number of permutations becomes 4 factorial. So 4 factorial represents the number of total arrangements of 4 letters. And if I divide this by 2 factorial, I get 24 divided by 2, which is 12. Okay, so to go from 24 permutations to 12 permutations, I simply take 4 factorial and divide by 2 factorial. Now, what if a letter repeats 3 times? So what are the permutations of LALL? Well, I have LALL, I have LLAL, I have LLLA, and I have ALLL. So out of the original 24 permutations of arranging 4 letters in a word, now only, how many this time? 4 of them are different. Okay, so since 3 L's can be placed in 3 factorial ways, the number of permutations is 4 factorial divided by 3 factorial, which is equal to 24 over 6, or I could say 4. So what's the general rule? The general rule is the number of permutations of a set of n items of which are identical is given by the number is equal to n factorial divided by a factorial. There's a missing thing of which a are identical. Okay, so a is the number of identical items in that set. So let's apply this rule. So suppose you have 5 green tiles, 1 yellow, 1 blue, 1 red, 1 purple, and 1 orange. How many different single line patterns can you make? Okay, so how many tiles do we have in total? Well, we have 10 tiles. And how many of them are identical? Well, we're going to say 5 of which are identical. And which ones are identical? Well, the green ones. So there are 10 factorial ways of arranging 10 tiles, but if 5 are identical, I'm going to divide by 5 factorial. Okay, and this is simply 10 times 9 times 8 times 7 times 6, which is equal to 30,240 permutations. Okay, so we can also apply this rule in a similar fashion to distinct objects in a fixed order. Okay, so this concept also applies when a number of distinct objects need to remain in a specific order. And the reason why you can apply to this rule is because you can make those distinct objects all very much the same object. Okay, so it would look like they are repeating. Now, example 2. How many permutations are there of the letters in the word explain if the vowels must be in alphabetical order? Note, position of letters may change so long as the order A, E, I remains. So we treat vowels as one since they cannot change order. So we're going to replace each with V, and V will stand for the vowel. Okay. So when we look at the word explain, EXPLAIN, I am going to replace them. This will become, replace every vowel with the letter V. So V, X, P, L, V, V, N. So the number of permutations will be permutations 7 factorial because we have 7 letters in the word explain, and I divide by 3 factorial because of the repetition of the V's, of the vowels. Okay, so remember the vowels just cannot change order. So this allows me to simply say, okay, this is the vowel. This is the vowel here, then the next vowel is here, the next vowel is in here. This is the order I'm going to put them in. So my permutations are 7 factorial over 3 factorial, which is 840. Okay. Example 3, how many permutations are there of the letters in the word explain if both of the vowels and the consonants must remain in their original order? So I'm going to say here V for vowel and C for consonants. So the word explain becomes V, C, 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 V, V, C. So vowel, consonant, 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 vowel, vowel, consonant. So what are the number of permutations? The number of permutations are 7 factorial over 3 factorial times 4 factorial, which is 35. Now, permutations with several identical elements. You can do the same thing. You can extend the same principle to permutations where there are multiple items that are similar. So the number of permutations of a set of n items containing A identical items of one kind, B identical items of a second kind, and C identical items of a third kind, and so on, is just taking n factorial, the number of items in your set, dividing by the factorials of each of the numbers of identical items in your set. Okay. So consider the word Mississippi. How many permutations are made with all the letters? So to calculate this, we simply look at 11 factorial, the number of letters in the word Mississippi, and divide by the number of identical elements. So 4 factorial because we have 4i's, 4 factorial because we have 4 s's in this word, Mississippi, and we have 2 factorial because of the repetition of the letter P, so 2 P's. Okay, and carrying this out will leave me with an answer of 34,650 arrangements. What about the ones that will begin with the letter M? Okay, so if we have to begin with the letter M, then M is no longer going to be counted in the letter. So no longer in the letter count. Okay, so therefore, we have 10 factorial over 4 factorial times 4 factorial times 2 factorial. So all that changes is the 11 becomes now a 10. 3,150 arrangements. Part C, what if we have to begin with a P and end with an S? So again, we are restricting one more time the total number of letters. So we only have 9 factorial letters. But because P and S are repeating letters, I have to now change the bottom as well. So I only have the I's repeating, so 4 factorial. And because there are only 2 S's, if I take out one S, I only have one S left, so there's nothing else to divide down there. And sorry, I should say about the P's. There are only 2 P's, so if I had divided by 2 factorial before, I'm no longer doing that. Same thing for the S's. So if I have 4 S's there, and I already have forced myself to end with an S, then I only have 3 other identical elements, those 3 S's left to determine. So I have 3 factorial ways to arrange those S's. So my bottom becomes 9 factorial over 4 factorial, 3 factorial, which is 8,520 arrangements. Example number 5, a hockey team ends its season with 12 wins, 8 losses, and 4 ties. In how many ways could these outcomes have happened? So the number of possible outcomes. So we have 12 plus 8 plus 4, so looks like 24. 24 possible items, possible outcomes, so 24 factorial ways to arrange those wins, losses, and ties. But because we have repeating items here, wins is the repeating, so we have to do 12 factorial for the wins. And then we have 8 factorial for the losses. And we have 4 factorial for the ties, giving us still a fairly large number, 1,338,557,220 possible ways these outcomes could have occurred. Possible ways these outcomes could have occurred.